We're continuing our discussion on the observations, and now we will discuss magnetic field. And magnetic field, analogous to electric field, is actually the force that acts on a unit magnetic pole, but magnetic poles cannot be isolated. How does one create a magnetic field? Remember that electric field is created by charges. Magnetic field is created by moving charges. So as we have seen in the previous video, a current carrying wire creates a magnetic field around it. It deflects a compass needle when it is brought nearby. So it is created by moving an electric charge, or it can be around a permanent magnet. So how do we draw the magnetic field lines? Magnetic field lines point away from the North Pole towards the South Pole. So you can see that field lines terminate on the South Pole and they emanate from the North Pole pointing towards the South Pole. So that's how the magnetic field lines are directed. Now remember that we have seen Earth is a permanent magnet, and when we put a compass needle, its north magnetic pole points towards the geographic north of the Earth, which is a magnetic south pole. Now, geographic North Pole is about 1300 miles away from the magnetic South Pole, which is at Hudson Bay, Canada. So it's not exactly pointing towards the geographic North Pole, but it's very close. So the magnetic South Pole is actually a little bit misaligned with the geographic North Pole, about 1300 miles away from the North Pole. It's on Hudson Bay, Canada. Now, why is Earth a permanent magnet? Earth's magnetic field is due to ions and free electrons circulating in the interior. So we have basically a molten metallic structure inside the Earth, which consists of ions and free electrons. And when the Earth spins around its axis, basically these molten structures, which contains the ions and free electrons, will circulate in the interior, and these moving charges will create a magnetic field. And also there will be, due to the thermal gradient from the outside crust of the Earth to the interior of the Earth, there will be convection currents as well. So we will have a motion of charges due to thermal gradients, and that will be carrying thermal energy from one place to the other. And as a result, basically Earth's magnetic field is due to the motion, the overall motion of these ions and free electrons, which is triggered by the spinning of the Earth that causes them to circulate, and convection currents. Okay, how do we define a magnetic field if we cannot isolate a magnetic pole? Since a magnetic pole cannot be isolated, we will define magnetic field B in terms of the magnetic force on a charged particle moving with velocity v. A charged particle moving with velocity v creates a magnetic field, so let's define it based on this observation. The force acting on a charged particle which carries a charge q moving with velocity v inside a magnetic field B is qv cross with B. So this force is proportional to the charge. So if the more charge we have, the more force we will feel. And if velocity vector is parallel to the magnetic field vector, the force will be zero. You can see that this is a cross product, so the force is always perpendicular to velocity vector and the magnetic field vector. If there is an angle between the velocity vector and magnetic field vector which is other than zero, an angle theta, then we will see that the force is proportional to sine theta, because this is a cross product. Okay. Now, how do we determine the direction of this force? So we have the right hand rule. Point your fingers in the direction of the velocity and then curl them around towards the direction of the magnetic field. The thumb points in the direction of the force. So that's called the right hand rule. For example, here, if the velocity vector is directed like this, if you point your fingers towards the velocity vector, curl them towards the magnetic field, your thumb points in the direction of the magnetic force, which is perpendicular to the plane that contains the velocity vector and the magnetic field vector. Now, is this force, this is basically based on a positive charge Q here. So the direction that we determine is for positive charge. If there's a negative charge here, Q is negative, then basically we still use the right-hand rule to find the direction of force, but if this is negative, the force points in the opposite direction. So we have to change the direction of the force, make it point in the opposite direction if the charge is negative. What is the magnitude of the force? It is QVB sine theta. So it's the charge, speed, the magnetic field multiplied by sine of the angle between the velocity vector and the magnetic field. Okay, so here we have talked about the magnetic field. It is created by moving electrical charges or around a permanent magnet. Magnetic field lines point from the North Pole towards the South Pole. Geographic North Pole is misaligned with the magnetic South Pole on Earth, 1300 miles away. Earth's magnetic field is created by moving ions and free electrons in the interior of the Earth, which is due to convection currents and the Earth's motion spinning around its axis. We define the magnetic field using the force acting on a charge. A point charge Q feels a force QV cross B inside the magnetic field B, which tells us that the force is proportional to the charge. If the velocity and magnetic field point in the same direction, they are parallel, then we will have zero force. If we see that the force is perpendicular to the plane that contains the velocity and magnetic field vectors. If the angle between velocity and magnetic field is theta, the force is proportional to sine theta. The direction of the force is found by using right-hand rule. Point 4 fingers of your right hand along the velocity vector, curl them towards the magnetic field vector, and the thumb points in the direction of B if the charge is positive. If the charge is negative, the direction of the force will be in the opposite direction. And the magnitude of this force is QVB sine theta.